Okay, on the example I want to look at on page 380 at the top of the page, it says all U.S. voters must register. And what we're going to do with the arguments today, instead of writing them in terms of P's and Q's, we're going to make Euler diagrams, okay, to decide if they're valid or not. And so the first one, it says all U.S. voters must register. Okay, anytime we have an all sentence like that, okay, we're going to put the stuff that is the all part, if you will. So this is going to represent our U.S. voters. Okay. And all U.S. voters are going to be in the circle register. Okay. So that's how we're going to draw a diagram anytime we have an all sentence. If you turn back to the previous page, there is 178. There's just kind of a general description of any time that we have an all sentence. Okay, if it's all A or B, we're going to draw the diagram as such. If it's no A or B, then they're not going to have any intersection at all. Okay. If there's some A or B, we're going to do an intersection, okay, but not one inside the other as such. And we're also going to put a dot here, and the dot is very important. We'll get to that in a minute when we talk about the sums. Okay. And then when we say some A or not B, if that's the sentence we're given, we're going to, again, we're going to draw an intersection between the two circles, and we're going to draw the dot, okay, in A but not in B, okay, when it says some A or not B. So these are going to be the general diagrams that we're going to draw, but our biggest issue is that we're going to have to combine some of these sentences, okay? Okay, so we're going to combine some diagrams as we go. Alright, so let's see how that's going to work in this first one. As I said, the first sentence was in your page 180, was at all U.S. voters must register. So we'll put the U.S. voters inside the register circle. And then it says in part, the second sentence says all people who register must be U.S. citizens. Okay, so all people who register, so that means everybody in the register circle needs to be a U.S. citizen. So that means we're going to have yet another circle out here for a U.S. citizen. Okay. All right, so both sentences were all sentences. Okay, so that means that whatever the A part is of the sentence needs to go inside the entire B circle, if you will. Now, the conclusion that they've drawn here, and our job here is to decide whether the conclusion is valid or not. Okay? The conclusion is that all U.S. voters are U.S. citizens. So if we look at the diagram, is there any chance that if I'm a U.S. voter, which means I'm in this group, okay, is there any chance that I'm not in the U.S. citizen group? No. Okay. So therefore, we would say that this argument would be valid. Okay. All right. Now, if you look at another one, we'll look at a different one. It's going to be kind of similar to this one, but we're going to see that it may or may not always be valid. In this particular case, it is. Okay. The next one, and this is on the top of page 181 for you, says all baseball players are athletes. So it's an all sentence, so I'm going to write baseball circle, athlete circle. So that would be my diagram for that part. All right, and then it says all ballet dancers are athletes. Now, that's a little bit different because if I write, I need to put ballet dancers inside the athlete circle also, but it doesn't tell me anything about the relationship between ballet and baseball, does it? Okay, so there's lots of different ways that we could draw that then. Okay, if all we know is that the ballet dancers have to be in the athlete circle, okay, we could draw the second part of our drawing as baseball, ballet. That could be a possibility. Both of those would be in the athlete circle. True? Okay. It could be that athlete and baseball and ballet have some overlap. It could be. We don't know because they didn't tell us for sure about what the relationship is between the two. Okay. We could have it so that baseball and ballet were inside each other one way or other. I could draw the fourth diagram as the same, but have ballet outside, baseball inside, but still all inside athletes. So it could be any of these. Okay. So to decide whether the argument is valid or not, we need to look at the conclusion and see what they are trying to say. And the conclusion is therefore no baseball players are ballet dancers. Okay. So that would be this diagram. True. This would show that. However, do we know that this is the right diagram for sure? No, it could be that, or it could be that, or it could be that. And all three of these, okay, would indicate that that's a false sentence. True? And one thing that you want to keep in mind here is that it's easier to prove something is invalid than it is to prove it's valid. Okay? Because all we have to do is show one of these three, okay, and we can say that that's invalid. All right? So even though one of them works, okay, three of them don't. True? And if one of the options doesn't work, then we go ahead and say that it's invalid. Okay? All right. So like I said, we could show in a case, okay, this is one case where that would be true, okay, but there's other cases where it wouldn't be. So therefore, it would have to be invalid. It's kind of like what we did with our P's and Q's. If we got all true, we would say it's valid. Okay? But if we got any falses whatsoever, then we would say it's what? It's invalid. Okay. Okay. Let's take a look at another one. This is the same page, bottom, page 181. It says all mathematicians are logical. So I'm going to have mathematicians, logical. Draw my initial part of my diagram. And then it says no poets are logical. So if it says no poets are logical, that means I got to have poets outside the logical circle. Fair enough? Okay. And so the conclusion, let's see if the conclusion is true. It says, therefore, no poets are mathematicians. Is there any way that I could have poets and logical be two separate circles, not intersecting at all, and have math and poets be intersecting? No. So there's no way I can draw this any other way. So therefore, that final sentence is what? It's valid. Okay. Questions so far? Okay. All right. Now I want to get to the uses of the sum. Okay. Remember the sum A, R, B, and sum A, R, not B. Okay, because those are ones where we need to use the dot notation. So if you would turn to page 183 at the very bottom. Gives us the same first part. Says some mathematicians are logical. Okay. Actually, it says all mathematicians are logical, I meant. So all mathematicians are logical, it says. Okay. And then in the second part it says some poets are logical. Okay. Some poets are logical. Now, I want you to think about what that might look like then if I write some poets are logical. If it's a sum situation, then there's going to be an overlap between the circles of poets and logical. Okay? And so if I were to write poets here, and remember if I write some are, that means the dot is going to be in the intersection of those two. Okay? And so if I draw my diagram like that, the question says, therefore some poets are mathematicians. Okay? Now remember, it's easier to show that it's invalid than it is valid. Okay? And so if I can draw one case that makes the first two sentences true, but makes the conclusion false, then I can say it's what? It's invalid. Okay? Because again, does this diagram show that some poets are mathematicians? No. Okay? In fact, it shows some poets are logical, but is there necessarily an overlap between poets and mathematicians here? No. Right, so again, easier to show it's invalid, okay, than it is valid. Okay, so if you can draw your diagram to make both the first two parts true and the second part false, okay, then you can go with invalid. Okay. All right. Let's see. Let's take a look at one last one, number 6 on page 185, top of the page. Another mathematicians are logical. So this one says, same thing in the first sentence, all mathematicians are logical. All right, and then it says Euclid was logical. So they gave us a specific person here, so anytime it's anything specific, okay, we're also going to use that dot notation. Okay, because really saying Euclid was logical is like saying someone is logical. Okay, some person is logical. So that's kind of like some notation. We don't need to make a whole circle for Euclid because Euclid is just one person. Okay, it's just one single individual. Okay, one single case. So instead of making another circle, we're just going to make a dot. But where can we put Euclid here? If all we know is that Euclid is logical, then he could go right here, couldn't he? Okay. And looking at the conclusion, it says, therefore Euclid is a mathematician. Okay, is Euclid a mathematician in our diagram? No. So we could say that that is what? Invalid. Okay. So again, key issue here when we have a one case like this, where it's not a sum or an all or a no. Okay, if we have one case, we're not going to make a whole circle for Euclid. We're just going to make him a dot. Make sense? Okay. Okay, so our work for today that we're going to be doing in section 3.8 is going to be exactly that, trying to draw some Euler diagrams to decide on whether or not the conclusion is valid or not. Okay, so we're going to practice that right